Hello, I am Edward Berman, and I'm going to be talking about unbiased estimators. As an overview, I'm going to give you a problem state, talk about why it's difficult, answer the problem, interpret it, and give a little bit of a derivation. So we have the following problem. If you have n independent samples of a normal distribution with unknown mean mu and unknown variance sigma squared, what are unbiased estimators for mu and sigma squared? This problem is difficult because we find that the maximum likelihood estimate is biased or sigma squared, so we must introduce a constant to correct for it. So the answer is that our estimate for mu is what we'd expect for an average. We sum up all the variables and divide by the number of samples. But for sigma squared, instead of dividing by n or n squared, as something we would expect, we divide by 1 over n minus 1. So we find that the MLE is unbiased for mu, but biased for sigma. So we may define a sample standard deviation that is unbiased, as opposed to the already established mathematical definition. This is all very hand wavy for now, but we will come back to this after the derivation, and you will see. So without further ado, let us prove this. Let us prove that these answers are in fact correct. So we claim the maximum likelihood estimate is unbiased for mu. Well, this would be the estimate given by the maximum likelihood estimate. So if we take the expected value of each, we find that it is consistent with what we would get. The expected value of mu is the expected value of this sum. We factor out the constant. These properties of summation, these cancel out, and we find that the expected value of mu hat is mu. Well, what about variance? Well, we claim that this is the unbiased estimator, and the approach is as follows. We'll start with a maximum likelihood estimate, so that it is biased. See that it is biased to do scalar multiplication by a constant. Define a new estimator that is the MLE multiplied by the reciprocal of the constant that is giving us the error. Confirm that this new estimator gives us the desired result. The MLE tells us that our estimator looks like this. So we test to see if it's true that the expected value of our estimate is in fact sigma squared. By the lemma that is below, this is not true. This is n minus 1 over n over sigma squared. And by the way, we will get to this at the end of the proof. But it's off by this constant n minus 1 over n. So if we multiply by n over n minus 1, then we will get the right estimate. So let's find a new estimator, sigma 2 hat squared, and that's equal to our old estimator times constant. So if we take the expected value of this, well, this is a constant, so we factor it out. We know the expected value of our first estimator, again by level 1, is n minus 1 over n sigma squared, so this cancels out and becomes sigma squared. So therefore, this is our unbiased estimator. It simplifies to sigma hat squared is equal to 1 over n minus 1 times the sum from I equals 1 to n, xi minus mu hat squared. But I kind of just pulled this out of thin air by introducing the lemma. So let's dive a little bit more in depth. Here is the lemma. It's a lot of algebra, which is why I decided to save it to the end. Basically, according to the maximum likelihood, the expected value of sigma hat squared is this. We expand this polynomial like so. We take advantage of the linearity of the sum and this constant. We find that this right here is equal to negative 2 mu hat squared. So we add mu hat squared to get negative mu hat squared. We multiply by n and then incorporate it into the series dividing by n. Again, more algebra. Taking the expected value of each of these, doing some algebra to show that n mu hat squared is equal to this, and that expected value of the sum of xi hat squared is this. Distribute this one over n, and we get this term. And so this is where it came from before. And so all we had to do to get an unbiased estimator is just introduce a new estimator, multiply by the reciprocal of this constant, and then, which is why we end up getting 1 over n minus 1, because the n's cancel here and here. So it becomes 1 over n minus 1 instead of 1 over n. That'll be all. Thank you so much for watching.